Hi, everybody. So this is the video for week 3. So just some reminders to start off. Our third homework is due on Monday at 11:59 p.m. You have a quiz on this video due Tuesday by 8:30 a.m. So just like every week. And then I want to point out that your first exam is not this coming Thursday, but Thursday, February 9th. So the Thursday after this coming Thursday. That will be in class. So I'll post a study guide for that on Canvas at the start of next week. And then the class on the Tuesday immediately before it, so on Tuesday, February 7th, that will be a review session, and we'll run it online, and it'll be recorded so you can watch it if you want to review something from it, or if you can't make it to the in-person class, or if you can't make it at the time. Okay, good. But that February 7th, February 9th, that's not next week. That's the week after next week. I just want to point that out now. So what were the key takeaways from this week? Well, you did, and really the main thing was to see how to do some basic computations of SAGE, especially with remainders and doing linear algebra. And for where we're going next, the main thing is just to know you can compute remainders easily in SAGE. So you can sort of use this percent sign to sort of compute this like remainders that just like show up, for example, when you do arithmetic in like the field of p elements. And we'll sort of build a lot more on that in the next couple of weeks, next few weeks. Good. So you sort of learned that those basic computing skills of SAGE. And then also, maybe you haven't started this yet, but as you sort of work through the homework, when you get to exercise 1.5, well, that asks you to work through the very short first chapter in the textbook, and you'll get some familiarity with how the textbook is set up, how it sort of incorporates SAGE cells inside of it. And so that will sort of be some useful takeaway from this week now, because now we're going to start from here on out following the textbook a little bit more closely. So speaking of that, let me let you know what we're doing this coming week. So we're basically going to cover chapters 2 to 4 in the textbook. Chapter 2, the main idea is about greatest common divisors and sort of something called the Euclidean algorithm for computing them. I'll say a little bit more about that because we're going to start saying just a little bit about that in this video, and then we'll go into more detail in class on Tuesday. On chapter 3, we're going to explore some examples of solving equations in integers and sort of how that's different than like solving equations in the rational and real numbers. And again, you'll have gotten some taste of that already in this sort of exercise 1.5, this when you sort of were looking at the textbook, this first chapter of the textbook. We'll talk about that a little bit more, and that will be also in class on Tuesday, and then some in the video next week. And then chapter 4, which we'll do mostly in class on Thursday, is about this notion of congruences. Basically, this is a generalization of the idea of like the field of p elements and doing sort of arithmetic up to taking remainders, but sort of setting it up in a little bit more general of a setting than just sort of these fields FP. But we'll get to that on Thursday. Right now, just I want to go over some quick basic notions and notation to make sure we're on the same page before class on Tuesday. So particularly I want to talk about division. So this here, I've written down theorem 2.1.1. When I write down a number like this, that means that's the number in the textbook. And this just says if I have an integer a and then I have a positive integer b, then I can always divide a by b like we did in elementary school to write a is equal to q times b plus r, where q is an integer and r is an integer such that 0 is less than or equal to r is less than b. Another way, there's a unique way to sort of write a to divide a by b and get a remainder. So here this q is the quotient and this r is the remainder, and this is just doing long division with remainders like in elementary school. So for example, a is 9 and b is 3. Whoops, that's not what I wrote here. B is 3, so a is 12. Yeah, so sorry, if a is 12 and b is 3, so we're dividing 12 by 3. Well, 12 is 4 times 3 plus 0. So the quotient is 4, the remainder is 0. If a is 17, b is still 3, then we get 17 is 5 times 3 plus 2. So the quotient is 5, the remainder is 2. You can also divide a negative number by 3. So if I sort of do this with a is equal to minus 5, then I get minus 5 is minus 2 times 3, that's minus 6, plus 1. So this remainder should be between 0 and 3. So when I have to sort of do a negative number, I have to go sort of down below it. So I sort of go down to minus 6 and then add 1 to get back up to minus 5. So here the quotient is minus 2 and the remainder is 1. Okay, so this is just some examples of how how division works, division with remainders. Let me introduce some notation. We say B divides A, and we write sort of B, this little midline, this bar A, if the remainder is 0. So we say B divides A, so when you divide it, sort of it divides it evenly. So just this classical notion of when one number divides another that you'll remember from your experience of numbers. So for example, if I look at number 12, well, 1 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12, and 12 divides 12, but 5 does not divide 12. So if you sort of draw this bar with a line diagonally through it, that means does not divide. So 5 does not divide 12. If I divide 12 by 5, the remainder is 2, not 0. Good. So that's just some notation for talking about when one number divides another. The next thing, actually the really important idea, and I think this is sort of surprising that this is an important idea, is going to be that of the greatest common divisor of two integers. So if I have integers m and n, the greatest common divisor is going to be the largest positive integer d that divides m and divides n. So if I, for example, I look at 39, 65, you can check that these are both divisible by 13, and that's sort of the largest positive integer that divides both 39 and 65. Good. So this is sort of a pretty, again, like a notion you'll remember from elementary school, and it's not a particularly complicated notion based on sort of our experience with mathematics. But it ends up actually sort of thinking about carefully of greatest common divisors will end up being a very powerful tool. And so what we're going to do in Tuesday is we're going to introduce this Euclidean algorithm, which gives you sort of an algorithm you can follow to compute the GCD of two numbers. Like you might say, well, to compute the GCD, I should just do the prime factorization and then look at sort of the prime factors that overlie. Let me point out that actually, like in this class, we don't actually even know, like you should sort of put yourself in a situation where we don't even know prime numbers and like we don't even know prime factorizations exist yet. So actually somehow like this Euclidean algorithm shows up when you prove, when you justify the statement that numbers have unique factorizations into primes, into prime factors. And so again, so this ends up being like a surprisingly rich idea, and we'll use this Euclidean algorithm for computing GCDs in quite a few ways. So just as one example we've seen already, this is sort of a difficult problem to sort of understand how to compute 1 over x when you have x in the field with p elements. So if I like asked you to compute like 1 over 7 in a field with 13 elements, like sort of when we talked about that, like the only way we had to do it was sort of guess and check. This will give you some way you can actually sort of find the solution in like in like sort of computationally like useful way, rather than just guessing and check. Okay, but that's all stuff we'll sort of start seeing in class on Tuesday. So I'll stop there and see you in class.